All right, so just as a brief review of some definitions that are important to remember, we have looked at the transfer or flux of x momentum, meaning the momentum related to velocity in x direction, across a y plane. I also call that in y direction. Y direction is across a plane that is orthogonal to that direction. So when I say transfer or flux of x momentum, and I'm thinking about the momentum perspective, how do we actually describe this flux, which I call tau yx? What is tau yx? And how does it actually get transferred? So I do take x momenta of my particles, and as they're colliding with each other, they're going to transfer. If I have higher velocity in one place, so I always go from higher velocity to lower velocities, or that's also higher momentum of particles to lower momentum of particles. Okay? So I'm basically moving from higher to lower, and I'm going to transfer it through interparticle collisions. Okay? And in this particular case, when I'm looking at tau yx, I'm looking at my x momentum related to vx that is moving across in this y direction or moving across a y plane. I could actually look at it in all other situations as well. Any difference in velocities that I have, I can actually look at the transfer. This was the specific situation where I only had Vx, so we put things in between two plates, parallel plates, and we were looking at the case where my only non-zero velocity was in x direction, so that's what's related to that. But in any general case, and we will generalize down the road, we're going to have all kinds of pairs of planes and velocities. Okay? Now, what is that from the force perspective definition? How do I look at this momentum transfer? So I kind of conceptually split my fluid into two different portions, and this faster portion is kind of pulling on the slower one. Net. If you look at the net force, there's a net force, and it's doing this. This is shear. Normal is this. Okay? So it's transfer. We will actually look at, of course, the contact forces in normal directions as well, but most of the time when I'm thinking about shear stress, this is the one that I'm thinking about. So I'm thinking of a force that this lower portion of fluid is per area, right? This force per area kind of a view. And in different conceptual situations, we will actually use one way or the other to actually explain something. Today, actually, we might get to use the force perspective. So we use this momentum transfer definition, and we were looking at gases at low density. We applied kinetic theory that simplifies my molecules to basically balls that are colliding with each other in an elastic way, and that's all that there is to it, to their interaction. And we actually derived, we arrived at a number of things. First, we applied this kinetic theory that was not related to Newton's observation, and we confirmed Newton's observation. That's an extremely strong result. And we also got a formula for viscosity that is not dependent on velocities itself, but just like on some fluid properties. So based on the formula we got, so this is just this definitions that we went through. So based on the formula we got, okay, based on this kinetic theory of gases, gas viscosity is proportional to 1 over t, square root of t, or t? Square root of t. So this is the type of how I want you to remember these, not the precise formula. If you want the precise formula, this is actually what it was. So P is just P. This is mass of the molecule. This is diameter. This is Boltzmann constant and the microscopic temperature. Okay. Now, and we actually did some massaging to that formula, so-called via so-called Chapman-Enskog theory, which added intermolecular forces into the mix and corrected the formula. So now we actually want to move on to liquids. Okay? And there are some common sense differences between liquids that everybody kind of knows. Gas is freely flowing and filling all the available space immediately. It kind of just occupies things. I can also compress it so it can easily expand, and I can also compress it, not necessarily easily, but it can be done. Okay? Whereas liquids have this, they're more cohesive in terms of molecules, they're sticking more to each other, and it's kind of flowing, so it means that molecules are pulling each other as they're moving along. And there's this free surface typically dividing it from any other phase that I might have. Gases typically don't, there's no such thing as gas-gas interface, right? They will kind of interdiffuse almost immediately. So there are certain stronger molecular forces that are in action within liquids that are not necessarily allowing them to easily mix with either other gases or liquids. And most of the gases, when in the presence of a surface, they're not necessarily wetting it, whereas some of the liquids do. And every time I have a gas and a liquid present, liquid is more wetting to a surface than the gas is. Yes?
What do you mean by wetting? Like, is it the conventional petrophysics definition of wetting and non-wetting, or
yeah.
is it like?
So that's what I'm thinking. So what I'm actually really thinking, again, it depends on the gas. But if I put a gas and liquid together close to the surface, in most cases, gas is the non-wetting one.
Okay, so petrophysics.
Okay. Yeah. So petrophysics definition. All right. So how does that affect me in actually trying to derive any theories? Well, these bouncing balls that are occasionally colliding with each other and otherwise are not interrelated are nowhere in this picture. I cannot apply kinetic theory to liquids and get anywhere. For one, we know that we have experimental observation that says that with increased temperature, my viscosity will decrease, and I know based on the kinetic theory that I got the opposite, so it doesn't apply. Even if I try to force it, it's not going to explain what I needed to explain. So the problem is this very strong intermolecular forces. Okay? They're not as strong as in solids as to have a cage that you can not possibly escape from, but they're pretty strong. And the way it's normally viewed is that you actually have this molecules that are in some sort of a loose cage, and there are some empty spots in this cage, and every once in a while a molecule will jump into an empty spot, and then the other one, there is a new spot opened, and the other ones will jump into that one. So there's this constant motion, even though I have like a liquid at rest, macroscopically it ain't going anywhere, there's these molecules that constantly rearrange themselves. Then if I actually expose this to shear, liquid doesn't shear, it just flows in response, okay? So I don't have like some small infinitesimal deformation in response, I just flow away, okay? So if I shear, then basically this ability to fill in these holes and create new holes will actually allow liquid to flow and kind of pull all of the other liquid with itself. So there's this sort of idea of vacant sites that we're going to fill in. And we're actually going to use that idea in actually deriving theory similar to gases. So just to recall what we did to derive formula for gases, and this is just a review, we put sort of liquid and gas in between two plates, and we had this idea, okay, I'm going to impose my difference in velocity, so I'm going to have one plate move at the velocity Vx and the other one stationary, so I have sort of a gradient in velocity applied. And then we actually looked at the kinetic theory and see what would the transfer of momentum in that case look like. Okay? And we assumed that my velocity so sort of linearly changes in my little element that I was looking at. And then we actually arrived at the formula. Now we will do somewhat similar here. So in liquids, I have now this loose cage, and there are some vacant spots in there. Okay? And we will look at there's a theory that really it tells me sort of based on how much energy it takes to jump into that spot. Okay? I'm gonna have a formula that tells me what is the frequency of these jumps. So what is basically statistically, what is the frequency of these jumps into a vacant spot? And I will actually, and I will have that for fluid at rest, and I will have that for fluid exposed to some shear stress. Okay. So when I compare the two situations, if I actually have any kind of momentum transfer, so basically I have a difference in velocities, and I know that that's going to cause the momentum transfer, I'm going to relate these differences in velocities that I see between the layers, I'm going to relate to the frequency of those jumps. Okay? Because obviously, if I have a shear force helping and pulling, there will be this shear force will help a little more. If I'm kind of in the same direction as my shear force, there will be more jumps in that direction, okay? Because basically the force will help those. So it's going to reduce the work that shear force is doing on the fluid, will reduce the energy that I need to jump into a vacant spot. Yes?
So your jump is essentially your collision in gases, right?
Well, it's not a collision. I kind of actually have to conceptually squeeze in between these two.
I'm saying the jump is taking the role of that the collision is in gas.
Yes, yes. So my collision there will still be some momentum transfer, but I'm going to relate it to those jumps as opposed to collisions, yes.
Do we have collisions?
Not really, not in liquid. Okay. Liquids guard themselves better against that because of these loose cages. Okay. So actually, to get in between two molecules, you need extra energy to squeeze in between because there's repulsive forces that are much stronger because molecules are much closer. Okay. So yeah, jumps are taking the role of collisions.
They're epoxy.
Yeah. Okay. So let's actually now do that. As I kind of told you the story in hand waving. Well, let's write the story down, and this will actually ultimately give us a formula for viscosity. All right, so I'm going to switch to my okay, works. All right. And I'm just going to make sure. Alright, so basically, again, if you see me doing some weird gymnastics here, I hope I don't disconnect things, but there are some chords here that are too short, so I'm gonna try not to collapse anything around here. So let's kind of first, so I'm gonna put the title, Molecular Theory of the viscosity of liquids. So I'm first going to draw myself this potential cage. These are my idealized molecules. And this here is what I'm calling a vacant spot. And I'm going to call this molecule 1. I'm going to kind of pay attention, what is it doing? And this distance, I'm going to call A. This is sort of the width of a basic cage, if you will. I'm going to call this layer A, layer B, layer C. And there's some separation between these layers, which I'm going to refer to as delta. This is a Greek letter delta. So now if I'm looking at the energy, so basically for this molecule to jump through, the way I'm actually looking at the energy of this molecule, so this is energy of this molecule 1. So it likes being in this position. It's right now here at the equilibrium. So relatively speaking, its energy is lower. Okay? And to actually squeeze through here, it needs higher energy. Okay? So basically, and then once it gets through this position, it's going to go back to lower energy again. Okay? Because it's sort of an equilibrium position it's trying to get to. You can also gonna look at this is basically, so if I have my energy, what I'm saying is that relative energy level is something like this. Okay, so these low points correspond to my equilibrium positions that I'm trying to get to. And if I'm ever so little disturbed, if I'm around this high energy level and I'm a little jiggled, I'm very likely to jump. So once I'm actually around here, I'm very likely going to jump to the lower energy level because that's more stable. Okay? So basically there is some height to this, and I'm going to call it delta G. Okay? This is my molar free energy of activation for escape from the cage. I'm calling this a cage in a stationary fluid. So basically this height here, molar means that it's per mole. So basically to get energy of one molecule, I'm going to divide by which constant? How many molecules in a mole? Called Avogadro. 6.022, I think, times 10 to the 23, is it? Yeah. We're going to have for jumping sort of downstream, so to speak. Right now, a positive sign means nothing, but we were going to have with the stream and against the stream, so I'm immediately saying plus. Now, what happens if I actually have a fluid in the movement? So basically, I'm going to have something helping me out here. Yes?
Is the energy in the vacuum
This is plus
high,
here.
or is the energy in the cage is high, then that's why all of the molecules go away from
No, you always want to minimize your energy in nature in general. You're always minimizing energy.
Yes.
So you kind of want to go to this position. So this really means that if you're ever so little disturbed from this position, you're going to immediately go into this neighboring site if it's open. Does that make sense?
This maximum and the maximum of the curve is the place that molecular is?
Right. So basically, if I actually want to go from here to here, I need to get this much energy, right?
I think what she was asking is that the maximum is at the point where it's exactly between the two molecules.
Yeah, yes. It's so I'm relating things to this. So this is my A, right? So it's related to this position. Maximum is related to this point. Sort of like a squeezing in between these two molecules. Because that's energetically the highest energy because there's a repulsion going on, right? So I need to overcome that. All right, so this is at rest. Now if I actually have some motion going on, let me choose a color here. I'm gonna go with this green. So let's say that I have motion and this layer is faster than this layer. and this one is faster than this layer. Okay. Then I have stuff helping me out to move in certain direction. So technically, it's gonna be easier if I'm going in the direction of the flow. It's gonna be easier for this molecule to go through this sort of tight spot as opposed to this spot. And the way I'm gonna depict that is that the difference between, so this is the energy that I have to actually jump through here, but now that barrier is gonna be smaller. So this difference is gonna be smaller. So it's gonna be easier for me to do so, okay? Whereas if I actually wanted to go upstream, so technically if I wanted to go from this spot to this, if this one was the vacant one and this one was the occupied one, it'll take me more energy, okay? So I'm gonna present that as this. So basically, if this would be my energy levels, again, these energy levels are to be looked at through differences in energy, not sort of necessarily in the absolute sense. So basically, then I have to overcome all of this to go upstream, okay? So this is downstream jump, activation for downstream jump. Okay, so this is if I have this shear force helping me out. Now let's formalize all of this, okay? And this theory is actually due to Eyring, this model of fluid movement. So first, some definitions I already introduced. A, this is my length of a molecular jump. And we're gonna introduce nu. So this is again Greek letter. I have a Greek here too. How would you say that?
This is N.
N. I said nu, but to differentiate from N.
It works.
It works. I have some confirmation. But when you were saying alpha, beta, gamma, delta, epsilon, zeta, eta, theta, in that thing you never say N, you say nu.
You say me.
Ni, okay? Ni. Let's go with ni. So this is my frequency of jumps. It's looked at as per molecule. Okay, and then I need more control open. Save. Everybody had a chance to write down? I'm about to change. Everybody good? All right. Okay. So then basically my energy, and also I will use some known constants here. So my frequency is given as kappa t, where kappa is my constant that I already introduced, and that is Boltzmann constant. The Boltzmann constant relates energy of a molecule to its macroscopic temperature, divided by h, which is Planck constant. Planck constant relates energy of the molecule to the frequency of some electromagnetic wave that it could produce. So I kind of don't know much more than that. But it's a basic constant in quantum mechanics, and this is going to be my exponential function of the energy of activation that I already introduced per mole, divided by RT, where R is gas constant, and kappa is
Boltzmann's, and H is Planck's. So we were just gonna take that as a given.
If this is a non-idealized liquid, would just adding Z in front of R do the trick?
Possibly, I don't really know, but possibly yes. That's a standard correction we do for. All right. Now, if I actually had a moving liquid, what happens? So let's say what happens in moving liquid. Philosophically, now I'm still thinking about the question. Philosophically, everything you can, to the first order, fix with a constant, a fixing constant in front or a coefficient. Okay, so what happens in a moving liquid? Let me look at this part where I'm about to, my main work needs to be done on getting the molecule to that neck in between two molecules, right? And the moment I'm there, I'm just gonna go to the next site that has lower energy, right? So that's the energy barrier I need to overcome. So if I actually have a sort of, if I imagine a little box of liquid, so this is the box of liquid of length A12. So it's basically from that position 1 to the bottleneck, energy bottleneck. How's that? Position-wise, okay? So now, how much is this shear stress acting on this little box? How much is it helping? Okay, let me quantify that. What is the work done by the force on this little box? Well, first, my box, I'm going to give it some dimensions. So I'm going to look at the box of size delta that's in between two conceptual molecular layers. Not that the cage distances, whatever they are. Okay. And then I also have the area here, A. Okay. So if I'm assuming that I have shear stress here, tau yx, or if it's a force, it's a tau yx divided by A. That's my force F. That's my shear force. Doing work on liquid.
This is multiplied by A, right?
Multiply, yes. I first wanted to write F, and then I imagined F over A, and then I changed my mind and wrote it. My brain works in mysterious ways. Okay. So this is my force. So essentially the work this force is doing, okay, is the force times the distance, which is this half A. So the work is 1/2 A times force, which is tau yx A. And I'm gonna not work with A, I'm gonna work with volume because we're also looking at other properties that are expressed per volume. So I'm gonna say 1/2 A tau yx, this volume divided by delta. Everybody agrees with me? Where V is A delta, it's a box volume. Okay, so if I had, now I'm looking at the energy barrier, okay, and I'm working on fluid, and let's say that I'm trying to jump downstream. Then essentially, as long as I had this molar energy of activation, so that's per molar volume, if I basically normalize this work per molar volume, I'm helping out that energy of activation with that work. And I'm going to assume that all of that work goes to helping my molecule to jump. Okay? I think I can assume that with a reasonable thing. So basically my energy of activation, and I'm going to look at it as a negative number because we had it as a negative in that exponential. It's what I had before at rest. And when I'm going in the positive direction with the fluid, I'm reducing it in absolute sense, right? So I'm just going to put a plus. And I'm just going to express this as a molar work, right? So I'm just going to normalize it the same way I'm normalizing the energy. So this is if jumping downstream. And if I had jumping upstream, I have to do that much, I have to have that much more energy as this work that I need to overcome. So it's going to be minus delta G minus. So this is going to become larger in absolute sense, and because of that,
why do you have the plus in the delta G? That is not a reference to the direction.
this is reference to going downstream. And this is reference to going.
I mean, on the right-hand side, you have plus in both.
Yeah, there was no downstream then. It's just the notation from literature. Okay, there was that question that was already confusing to somebody else. It's just the way notation is. Okay, so now I'm gonna say, if I'm gonna use, instead of this original here, let me change colors. If I have this, I'm gonna replace with this to get the frequency of downstream jumps. Okay, and this thing I'm going to replace with this term to get the frequency of upstream jumps, and I'm going to refer to them as a Ni plus and Ni minus. Okay, so that's going to be sort of plus minus, so to speak. Okay, I'm just going to replace with these two. So I'm going to rewrite that. I was just trying to visualize. So I'm going to replace this stationary term with one of the dynamic terms, either plus or minus. And that's going to give me the frequency of downstream jumps versus the frequency of upstream jumps, which are not the same anymore because the liquid is not stationary. Alrighty, so is everybody done writing things down? Yes? All right, so basically it's going to be plus minus frequency of forward or backward jumps, or downstream or upstream, however you want to call them. And that is going to be essentially divided by h exponential of first that term that I had before plus minus, okay? And I'm going to basically replace my work, the full formula, if you will. I'm just going to actually call it like this. To shorten my writing. I derived what W is. I'm going to use it down the road. Okay. So I derived the W in terms of A and tau yx and all that. Okay. So-
Just to be clear, so for the downstream jumps, it'd be minus work over RT?
If you plot because it's the exponential with the negative in there, and then you'll see that it's a little counterintuitive. You have to think about it, but if you plot the function, you'll know it. Because ultimately, you look at kind of at absolute values and what are they doing. Okay, so now I'm blaming this shear force for basically my extra velocity or velocity differences that I have between the layers, okay? So now if I'm thinking about it, I'm also blaming this shear force for this extra jumps that I get that go downstream, and that's actually what's pulling my fluid to flow downstream, okay? So essentially I can relate the two. So if I'm thinking about the difference between the two layers, okay? So if I'm looking at the velocity difference, for instance, that there was that layer A, layer B, layer C. So the velocity difference Vxa minus V or VA, if you will, Vx in layer B. So this is higher than the first one is higher than the second one. So I'm going to call that delta velocity. So basically blame it on extra jumps, extra molecular jumps. And this frequency is in 1/2. Okay? And each jump I'm thinking is length A. Okay? So basically it's actually A times the difference between how many more do I have between the two, which is, this is my net number of extra jumps downstream. Okay, some of them are going upstream.
Why is it not A by 2? Because you're not doing extra work as A over 2, right?
Yeah, but I will have jumps just happen once you're past. Yeah, yeah. Once you're past that point, it's just going to happen. Yeah. It doesn't have, energetically, it doesn't matter. It's just going to happen. So I'm still in box of, and my jump will be of A. So once I'm past the energy barrier, which my energy barrier is at A half, but once I'm past that and have enough energy for that half, I'm going to jump all the way A. I'm not going to stay in that neck there, right? And again, some molecules will be stupid enough to go upstream. More of them will go downstream, right? And it's the net difference that is actually responsible for the velocity difference.
Why are they going
Relative.
up? Why are they going up? Like, what's the reason?
They might have the energy on that spot, so you
Where
still
do
have some
they get it?
randomized motion.
Where do they get the energy to go against the stream?
So they might just have, like, yeah,
Besides-
you have distribution of energy. Yeah, so some of it will still happen. And there is some inertia, so you impose, like if you didn't have, they would go everywhere, right? So there's some tendency to go everywhere, and if I have enough energy and there's a vacant spot, I might go there, okay? Just because it's easier to run down the hill, that doesn't mean that I cannot run uphill. I might have had a good lunch and have enough energy, yes?
That difference between the two layers,
Mhm.
velocities, is attributed because of the difference in the net jumps, right?
Yes. Because when I take the net jumps, I'm gonna kind of basically cancel out what I would have in stationary liquid, which is kind of my resident or background velocity, if you will.
So in this case, you should have A and then multiplied by the net jumps in layer A minus the net jumps in layer B.
Yeah, but it's kind of the same in every layer. The differences. So if I have some sort of background absolute velocity that I'm relating to, right? This extra shear pull will do extra jumps. Relatively speaking, I will still have velocity go lower and lower and lower as I go up in absolute sense.
So here we don't need a subscript on the right hand side, or no?
No, we don't. No, because the actual, so that's what I will call background velocity of around that layer is the same and cancels out.
Okay.
Right. All right. Okie dokie. So then what is my dvx dy, which I'm somehow, somewhere hoping to relate to tau yx? Okay. dvx dy by definition is approximated as vxb minus vxa, because my b layer was in y direction, higher in y than a, divided by delta. So that's my minus delta v divided by delta. So this is minus a over delta times this net frequency. So my minus dvx dy is equal to a over delta times. Now I'm going to plug in these formulas. And I'm going to remember when I have exponential, then this exponential of this sum is an exponential of the first term times exponential of the other term, right? So basically what I have, this is what I had in front of both ni plus and ni minus. And I can actually take that common term out, and then what's left is exponential. I'm going to still write it as minus exponential of minus and we will remember that sine h, or hyperbolic sinusoidal function, is 1/2 of So this term is essentially 2 sine h of and actually I can then write what W is. It's 2 sine h of a tau yx. Instead of volume, I'm just going to put molar volume to go from W to W tilde. Tilde is molar. Times 2 delta RT. So this is when I replace W. W was this. So I basically, in the W, to get W tilde, I just used molar volume instead of. Alrighty. Now, when I actually see what am I trying to compare in this whole thing? I'm trying to get the expression for tau yx is equal to some minus coefficient times dvx dy. Do I have that? I do? Somewhat, somehow. This is where engineering analysis comes to rescue. All right, so I have tau yx is within this sine h term, okay, in here. And then I have some stuff. This would be a good candidate or part of the candidate for viscosity, right? And then I have dvx dy here. So I have to somehow pull out tau yx out of this nonlinear relationship. Okay. Everybody sees that? I'd like the relationship to be tau yx equals to minus viscosity times dvx dy. Yeah? So in order to do that, I actually have to get this out. Okay. Otherwise, I don't have a linear relationship. Well, in certain cases, I can actually do that. So and we will get the chance to do it just before the end of the class. So basically, if we can remember, or you will remember even better than I will, that sine h is equal to x plus 1 over 3 factorial x to the cube plus 1 over 5 factorial x to the 5 plus, okay? So it's sine h, this is approximately x if x is much larger than 1. I can basically ignore all of the higher order terms. Okay. So assuming a tau y x v tilde over 2 delta RT is less than 1. So for relatively small shear stresses, okay, we can approximate sine h x as x. And then indeed, I will get that minus dvx dy is approximately a over delta kappa t over h exponential of that first static term. And then just instead of sine h, I just forget sine h, but it's 2 times sine h of x, and this x was actually a tau y x v tilde 2 delta RT. So I can actually then express tau yx when I clean this up as minus something, which I'm going to call viscosity times dvx dy. Yes. So basically my tau yx is going to be minus, and I'm just going to put the clean term down, delta over a square r over kappa h over v tilde exponential of delta g0. Note that this went from minus to plus because I put it from the denominator up, and dvx dy. And it's this that is my viscosity term that doesn't have any velocity terms in there, just some sort of stuff that is related to the fluid and the condition it's in. This is actually Avogadro's constant here. Now this is simplified in the various ways. There is problem is how do I actually measure this, okay? So in order to measure, I have to be able to measure this energy, which is not necessarily related. So the way it's done, you can measure some molecular forces, and basically you have to throw in some models and correlations. So there's various expressions that are similar to this. Sometimes it's actually, so some other approximate forms that try to relate this to something that I actually have tabulated are as follows. One is that mu is Avogadro's number h divided by molar volume, exponential of 0.408 delta. This is internal energy of evaporation divided by RT, and this is something measurable. Or sometimes also exponential 3.8 critical temperature divided by T. in either way, the way to remember this really is constant A exponential of constant B divided by T. So general form. So form to remember is that mu is A B over T. Okay? And having in mind that this is derived for a relatively idealized theoretical case, often if you're looking for, you have experimental measurements that you want your prediction to be more realistic, this is something that you're going to fit your experimental data to. Okay, even if you don't have this direct molecular level measurements. All right? So this is the form to remember. All right. Thank you for allowing me to finish the class.